The universe has no global picture. There's no God's eye view, no view from nowhere, no objective description that captures everything about the universe at once. This isn't a limitation of our knowledge or our technology. It's a fundamental feature of reality itself. After decades of working on quantum mechanics, relativity, black holes, and cosmology, I've come to realize that the very idea of a global picture of the universe is incoherent. It's not just that we can't have one. It's that such a thing cannot exist, even in principle. Let me tell you why this is true and what it means for how we understand reality. When I was younger, I assumed there was an objective reality out there, independent of observers. The universe has a definite state at each moment. Maybe we don't know that state completely, maybe we can never know it, but it exists. There's a fact of the matter about what's happening everywhere in the universe right now. This seems obvious, intuitive, built into how we think about the world, but it's wrong, and physics has been telling us it's wrong for more than a century. We just didn't fully appreciate what that meant. Let me start with special relativity. Einstein showed us in 1905 that simultaneity is relative. Events that happen at the same time in one reference frame happen at different times in another reference frame, moving relative to the first. Think about what this means. Right now, from your perspective, there's a set of events happening simultaneously across the universe. That's your now, your slice of space-time, your global picture at this moment. But someone moving relative to you has a different now. Their slice of space-time, their global picture at this moment, includes different events. Some events you consider future, they consider present. Some events you consider past, they consider present. Which global picture is correct? Which is the real now for the universe? The answer is neither and both. There is no preferred reference frame. There is no absolute simultaneity. There is no objective global now. Every observer has their own notion of simultaneous events, their own global picture at each moment, and these pictures disagree with each other. They slice up space-time differently. There's no single objective global picture that all observers agree on. The universe has no global picture because now is observer-dependent. There's no fact of the matter about what's happening right now across the entire universe, independent of who's asking. Now, you might think this is just about reference frames, about coordinate choices. Maybe there's still an objective four-dimensional space-time and we're just slicing it differently. The global picture exists in 4 dimensions, even if our 3-dimensional slices disagree. But general relativity makes even this more complicated. In curved space-time, in the presence of gravity, there's no natural way to define global time at all. Different observers in different gravitational fields experience time differently. Near a massive object, time runs slower. This is not just an observational effect. It's a real difference in how much time passes. If I hover near a black hole for an hour while you stay far away, you might age by years. We genuinely experience different amounts of time. So whose time is the correct one for defining a global picture of the universe? The answer is that there is no correct choice. Time is local, not global. Different regions of space can have different time coordinates, and there's no objective way to synchronize them universally. In cosmology, we often use something called cosmic time, defined by the expansion of the universe. Observers at rest with respect to the cosmic microwave background all agree on cosmic time. This gives us a useful global time coordinate for cosmology. But this is a convenience, not a fundamental feature of reality. It works because our universe happens to be homogeneous and isotropic on large scales, but it's not universal. An observer falling into a black hole doesn't experience cosmic time. Their proper time is completely different. There's no global time coordinate that works everywhere in the universe, that all possible observers agree on. Time is inherently local, observer-dependent, tied to particular reference frames and world lines. The universe has no global picture because there's no global time to define what at one moment means. Now let me tell you about something even more fundamental. Quantum mechanics destroys the notion of a global picture in a more profound way. In classical physics, even with relativity, you could imagine that the universe has a definite state at each space-time point. Maybe different observers disagree about simultaneity, but at least each event has definite properties. The electromagnetic field has a definite value here, particles have definite positions and momenta there. Quantum mechanics says no. Before measurement, systems don't have definite properties. They're in superpositions, existing in multiple states simultaneously. An electron doesn't have a definite position until you measure it. It has a wave function, a cloud of probability. Now, you might think we could still have a global picture, the global quantum state of the universe, the universal wave function. This wave function describes everything, everywhere, at the fundamental quantum level. But here's the problem. The wave function is not observable. You can't measure it directly. And when you do make a measurement, from your perspective, the wave function appears to collapse. The system goes from being in a superposition to being in a definite state. But this collapse is observer dependent. Different observers making different measurements see different collapses, different apparent states. What looks like a definite state to you might still look like a superposition to me. In the many worlds interpretation, there's no collapse. Instead, measurements cause the universe to split into branches. Each outcome happens in a different branch. You experience one branch, I experience another. But if that's true, then we don't share the same universe anymore after the measurement. We're in different branches of the wave function. My global picture includes my branch. Your global picture includes your branch. And these are different pictures. There's no single global picture that encompasses both branches that captures the full quantum state from all perspectives. The wave function itself exists, but it's not a picture any single observer experiences. It's an abstract mathematical object, and different observers experience different slices of it. The universe has no global picture because quantum mechanics makes the state of the universe observer-dependent, branch-dependent, measurement-dependent. Let me tell you about another reason, the holographic principle. I've spent much of my career on this, and it completely changes how we think about global pictures. The holographic principle says that all the information in a volume of space is encoded on the boundary of that volume. For a black hole, everything inside is encoded on the two-dimensional event horizon. For the universe, everything in our observable universe might be encoded on the cosmological horizon. Now, here's the key insight. The interior and the boundary are not two separate descriptions that exist simultaneously. They're complementary descriptions of the same physics. You can use the boundary description or the interior description, but not both at once. This is like black hole complementarity. An observer outside a black hole sees things in terms of horizon degrees of freedom. An observer falling in sees things in terms of interior geometry. Both are valid, but they're incompatible. You can't have both perspectives at once. If the universe is holographic, the same applies. You can describe it from the boundary perspective in terms of quantum information on a lower dimensional surface, or you can describe it from the interior perspective in terms of three-dimensional geometry and matter. But there's no global picture that combines both. There's no view that's simultaneously the boundary view and the interior view. They're complementary, mutually exclusive ways of describing the same underlying physics. The universe has no global picture because the holographic principle gives us multiple complementary descriptions, but no single unified view. Now let me connect this to cosmology and the horizon problem. Our universe has a cosmological horizon, a boundary beyond which we cannot see due to the finite speed of light and the expansion of space. Light from beyond this horizon hasn't had time to reach us yet and never will. This horizon defines the edge of our observable universe. Everything beyond it is causally disconnected from us. We can never receive information from beyond the horizon, never interact with anything there, never observe it in any way. So what does it mean to ask about the global state of the universe, including regions beyond our horizon? From our perspective, those regions don't exist in any operationally meaningful sense. We have no access to them, no information about them, no way to verify claims about them. Different observers in different locations have different cosmological horizons. An observer a billion light years away has a different horizon than ours. They can see things we can't, and vice versa. Their observable universe overlaps with ours, but is not identical. So whose observable universe is the universe? Whose horizon defines the boundary of reality? There's no objective answer. Each observer has their own horizon, their own observable universe, their own accessible information. There's no global picture that encompasses all possible observable universes for all possible observers. Reality is fragmented into observer-dependent patches, each causally disconnected from the others. The universe has no global picture because horizons fragment reality into disconnected regions, and different observers have different horizons. Let me tell you about quantum entanglement and how it further complicates global pictures. When two particles are entangled, they're not separate independent systems. They're part of a single quantum system that cannot be factored into separate parts. The quantum state of entangled particles is a state of the pair, not of the individuals. You can't describe one particle without reference to the other. There's no separate fact of the matter about the state of each particle individually. Now, everything in the universe is entangled with everything else to some degree. You're entangled with the air around you, with the photons bouncing off you, with the gravitational field you're immersed in. The universe is a vast web of entanglement, everything connected to everything else. This means you can't cleanly divide the universe into separate subsystems with independent states. Any division is artificial, approximate, ignoring the entanglement across the boundary. A global picture would require specifying the state of every part of the universe independently. But quantum entanglement means there are no independent parts. Everything is connected, correlated, entangled with everything else. You can't have a global picture made up of local pieces because the pieces aren't independent. The state of the whole is not reducible to states of the parts. The universe has no global picture because quantum entanglement makes reality holistic, non-decomposable into independent parts. Now let me address something that might seem to contradict what I'm saying, the wave function of the universe. In quantum cosmology, we try to write down a wave function for the entire universe. This seems like a global picture, the ultimate complete description. The Wheeler-DeWitt equation is supposed to describe this universal wave function. It's a quantum mechanical equation for the state of the entire cosmos. But here's the problem. The Wheeler-DeWitt equation has no time in it. It's a timeless equation. The wave function of the universe doesn't evolve in time. It just is. Time emerges only when you divide the universe into subsystems, when you treat part of it as a clock and the rest as the system. Different divisions give different notions of time, different ways the state appears to evolve. So even if the universal wave function exists, it's not a picture in the ordinary sense. It's not a description of what the universe looks like at a particular time, because time itself is emergent, division-dependent, observer-dependent. The wave function is timeless, and extracting a time-dependent picture from it requires making choices about how to divide the universe, what to treat as a clock, what perspective to adopt. Different choices give different pictures. There's no single objective, time-dependent global picture even at the level of the universal wave function. The universe has no global picture because even the wave function of the universe is timeless, and time-dependent pictures are observer-dependent extractions from it. Let me tell you about the problem of quantum measurement in cosmology. In ordinary quantum mechanics, we say measurements cause wave functions to collapse, superpositions to become definite states. But this assumes an external observer, someone outside the system who measures it. For the universe as a whole, there's no external observer. We're all inside the universe. So who or what collapses the universal wave function? What makes the quantum state of the universe definite? The answer is that it doesn't become definite globally. It becomes definite locally from the perspective of observers within it through decoherence and entanglement with the environment. But different observers with different states of knowledge, different histories of interaction with their environments, see different apparent collapses, different definite states. There's no global collapse, no moment when the entire universe snaps from quantum to classical. It's always a local, observer-dependent phenomenon. Different observers have different classical worlds emerging from the quantum substrate. So even if we talk about the classical universe, the apparently definite state of matter and geometry we observe, this classical picture is observer-dependent. It's not a global feature of reality, but a local emergent phenomenon. The universe has no global classical picture because classicality itself is observer-dependent, emerging locally through decoherence. Now let me connect this to black holes and the information paradox. When something falls into a black hole, there are two incompatible descriptions. From outside, it stays at the horizon forever. From the infalling perspective, it crosses through to the interior. These descriptions disagree about basic facts. Did the object cross the horizon or not? Is it inside or on the surface? Is there even an interior? Black hole complementarity says both descriptions are valid but complementary. You can't use both at once. The physics doesn't allow a global picture that includes both the exterior and interior perspectives simultaneously. This is not just about black holes. If the holographic principle is universal, the same complementarity applies everywhere. Interior and boundary descriptions are always complementary, never globally compatible. The universe has no global picture because complementarity, learned from black holes, prevents us from having simultaneous interior and boundary descriptions. Let me tell you about the arrow of time and how it affects global pictures. Time flows in one direction for us. We remember the past, not the future. Entropy increases. Eggs break, but don't spontaneously unbreak. But this arrow of time is not fundamental. The microscopic laws of physics are time symmetric. They work the same forward and backward in time. The arrow emerges from the fact that the universe started in a low entropy state and is evolving toward higher entropy. But this means the arrow of time is thermodynamic, statistical, emergent. And it's not necessarily the same everywhere. In different regions of the universe, with different thermal histories, the arrow might point in different directions. Near a black hole, the arrow of time becomes weird. Time and space exchange roles inside the horizon in a sense. The singularity is not a place, but a moment in time you can't avoid. In the early universe, near the Big Bang, the arrow of time might be different or undefined. The notion of past and future might not even make sense in that regime. So even the direction of time, past versus future, is not globally consistent. Different regions might have different arrows, and in extreme conditions, the arrow might not exist at all. A global picture requires a consistent notion of time flow across the entire universe. But the arrow of time is local, emergent, environment dependent. There's no global arrow. The universe has no global picture because even the direction of time is not globally consistent. Let me address something philosophical, the block universe view. Some physicists, taking relativity seriously, argue that the universe is a four-dimensional block. Past, present, and future all exist equally. Time is just another dimension like space. In this view, there is a global picture. The entire space-time, all of history, laid out as a four-dimensional structure. This seems to contradict what I've been saying. But even the block universe doesn't give you a true global picture. First, it requires a choice of how to slice the block into space and time, and different observers make different choices. The block exists, but what counts as now is still observer-dependent. Second, the block universe is a classical concept. In quantum mechanics, there's no single definite history, no unique space-time geometry. There are quantum superpositions of geometries, different possible histories interfering with each other. The block universe might exist in some abstract sense as the collection of all possibilities, but no observer experiences the whole block. Each observer experiences one branch, one history, one slice through the quantum possibilities. Third, the block universe assumes space-time is fundamental, but if space-time is emergent, as holography suggests, then the block is itself an emergent description, not the fundamental reality. The fundamental reality is quantum information, and the block emerges from it for certain observers in certain limits. The block universe doesn't give us a global picture. It gives us an abstract mathematical structure that different observers slice differently and that emerges from something more fundamental. The universe has no global picture even in the block universe view because slicing is observer-dependent and the block itself is emergent. Now let me tell you about the multiverse and eternal inflation. In eternal inflation, our observable universe is just one bubble in an eternally inflating space. New bubbles are constantly forming, each with different physical properties, different laws of physics even. If this is true, what's the global picture? Is it all the bubbles together? But the bubbles are causally disconnected. They can't communicate, can't interact, can't be observed by each other. So the global picture would include vast regions that are completely inaccessible to any observer. What does it mean to include them in reality? In what sense do they exist if they're fundamentally unobservable? And in eternal inflation, new bubbles are forming all the time. The multiverse is not a static structure, but an eternally growing, changing, fractal-like entity. There's no final global picture because the structure keeps growing forever. Even if you tried to describe it mathematically, you'd face the problem that different bubbles have different notions of time, different speeds of time flow, different measures on infinity. There's no natural global time coordinate for the multiverse. The universe, or multiverse, has no global picture because it's an eternally growing structure with causally disconnected regions and no global time. Let me connect this to something very practical. The measurement problem in many worlds. If the many worlds interpretation is correct, every quantum measurement causes the universe to split into branches. Each outcome happens in a different branch. After a measurement, there's no single universe. There are multiple branches, and you experience one of them. Different versions of you experience different branches. What's the global picture? Is it the entire branching structure, all possible worlds, but you only experience one branch? The global picture includes all the other yous in other branches experiencing different outcomes. This global picture is not something any observer experiences. Each observer sees one branch, one history, one apparent universe. The full branching structure is an abstract mathematical object, not an experiential reality for any observer. And the branching is continuous, happening at every moment, for every quantum interaction. The structure is unimaginably complex, with branches upon branches upon branches growing exponentially. There's no practical way to describe or think about this global branching structure. Each observer necessarily has a limited branch-specific view. The global picture, if it exists, is inaccessible. The universe has no global picture because quantum branching creates an exponentially growing structure that no observer can comprehend or experience globally. Now let me address what this means for the laws of physics. We usually think of physical laws as global rules that apply everywhere to everything at all times. Newton's laws, Maxwell's equations, Einstein's equations, they're supposed to be universal. But are they? In different regions of an eternally inflating multiverse, different effective laws might apply. Different vacua and string theory give different physics. The constants of nature might be different in different bubbles. So the laws aren't global. They're local, bubble-specific, dependent on the vacuum you're in. Even within our universe, the laws might be emergent, not fundamental. If space-time is emergent, then Einstein's equations are emergent laws describing emergent geometry. The fundamental laws govern quantum information, and Einstein's equations emerge as effective descriptions in certain limits. So there are no global fundamental laws that apply to all perspectives, all observers, all branches, all bubbles. There are local emergent laws, valid in certain domains for certain observers. The universe has no global picture because even the laws of physics are not global and absolute, but local and emergent. Let me tell you why I find this profound. We've been searching for a theory of everything, a single set of equations that describes all of physics everywhere. The ultimate global picture encoded in mathematics. But what if there is no such thing? What if reality is fundamentally perspectival, observer-dependent, complementarity bound? What if global pictures are impossible in principle? Then the search for a theory of everything needs to be reconceived. We're not looking for a global description. We're looking for rules about how local descriptions relate to each other, how different perspectives connect, how observer-dependent pictures arise from underlying quantum information. The theory of everything is not a global picture. It's a framework for understanding how local pictures emerge and relate. This is what ADA-CFT gives us. Not a single description of the universe, but a duality, a relationship between complementary descriptions. The boundary and the bulk are two views of the same physics, neither more fundamental than the other in a practical sense. The ultimate theory might be like this: a set of dualities, complementarities, relationships between perspectives, rather than a single God's eye view. The universe has no global picture, and the ultimate theory respects this by being a theory of relationships between perspectives, not a single global description. Now let me address what this means for us as observers. We can only ever have a local picture. We're embedded in the universe, not outside it. We have a limited view, a particular perspective, access to only a finite region of information, and that's okay. That's not a limitation to overcome. That's the nature of reality. Being an observer means having a perspective, which means not having a global view. Our science is necessarily perspectival. We make observations from our location, our reference frame, our branch of the wave function, our bubble in the multiverse. We develop theories that describe what we can observe from where we are. And these theories are incredibly successful. They make accurate predictions about everything we can measure, but they're theories from our perspective, not global theories. Other observers in other locations, other frames, other branches, other bubbles would develop different theories, equally valid from their perspectives. The theories might disagree on some things, but that's okay. They're describing different observable universes, different slices of reality. The universe has no global picture, and we as observers can only ever have local perspectival pictures. That's not a bug, it's a feature. Let me tell you about one final reason the universe has no global picture. The universe includes itself. Any description of the universe includes the describer, the observer, the physicist making the description. You can't step outside the universe to describe it objectively. You're part of what you're describing. Your brain state, your memories, your measurements, they're all part of the universe you're trying to describe. This creates a self-referential loop. The description includes the describer, but the describer is creating the description. There's no fixed point, no objective view from outside. It's like trying to draw a map that includes the map itself, or write a book that contains itself as a character. Self-reference creates paradoxes, incompleteness, observer dependence. Gödel proved that mathematical systems can't completely describe themselves. Any sufficiently complex formal system contains true statements that can't be proven within the system. Self-reference leads to incompleteness. The universe is self-referential in a similar way. Any global picture would include the observer creating the picture, which creates a self-referential loop that prevents completeness. The universe has no global picture because self-reference makes complete self-description impossible. So where does this leave us? What should we conclude from the fact that the universe has no global picture? First, we should abandon the idea that there's an objective, observer-independent reality that we're trying to discover. Reality is fundamentally perspectival, observer-dependent, complementarity bound. Second, we should recognize that all our theories are local, valid from particular perspectives, not globally true descriptions. This doesn't make them wrong or useless, just limited in scope. Third, we should focus on understanding relationships between perspectives, how different observers' pictures relate to each other. What's universal across all perspectives, even if no global picture exists? Fourth, we should embrace complementarity. Sometimes there are multiple incompatible descriptions of the same physics, and that's okay. They're complementary aspects of reality, not competing theories, one of which must be wrong. Fifth, we should be humble. We're part of the universe, we're studying, we have limited perspective, we can never have the God's eye view, and that's fine. We can still do physics, still make predictions, still understand our corner of reality. The universe has no global picture, and that's one of the deepest truths about reality that physics has discovered. It changes how we think about everything, from the nature of time to the meaning of measurement to the goal of physics itself. I've spent my career grappling with this, trying to understand what it means, how to do physics in the universe without a global picture. And I've come to see it not as a limitation, but as a feature, not as a problem, but as the solution to many problems. The universe has no global picture. And recognizing this is essential for understanding quantum mechanics, relativity, holography, cosmology, and the deepest nature of reality itself.